I'm Fiaz Ahmed. I'm a researcher here at UCLA AOS. And this is work that's slightly different from the talks we heard previously in the session, in that it doesn't have anything to do with numerical modeling, but more the focus is on simplified idealized modeling. And as we'll see, Dr. Arakawa's insights have a lot to say about models of this class also. And yeah, so my co-authors in this work, David Nealon, Spencer Hill, Kathleen Skiro, and Hui Su, and acknowledging DOE for the funding. All right, diving right in. So the ITCZ, defined as regions of the tropics that exhibit time mean ascent, and as a consequence is also time mean heavy precipitation. And the plot on the top left, you can sort of see the ITCZ you can view the ITCZ as a heat map of heavy precipitation here. So a band stretching across the Pacific and over the Atlantic, and somewhat broader regions over the Western Pacific and the Indian Ocean. And as maybe many of you might know, the ITCZ narrows and intensifies under global warming. This we know from climate modeling experiments, as well as just some proxies from the observational record, notably precipitation. And so what do I mean by narrow and intensify? It means that the area occupied by the ITCZ decreases in a warmer climate, and also the precipitation per unit area goes up in a warmer climate. As a consequence, the ascent that must balance the condensational heating also increases in intensity. So all of these are pretty robust, or I should say fairly robust properties that we can both simulate and somewhat observe. The question then is why does the ITCZ narrow? And this question has received a lot of attention in the past, I would say 5 or 6 years, a renewed attention. And the most notable contribution here is this energetic framework from Mike Byrne and Tapio Schneider, which essentially says start with the atmospheric energy budget and then divide the tropics into 2 zones, the ascent zone and the descent zone, and then write the energy budgets for these 2 zones, and then you manipulate the expressions, and you can derive this implicit expression for the ITCZ area. And essentially, from this implicit expression, you can reason as to why the ITCZ area narrows under warming. And the simple one-line explanation from this line of work is that under global warming, the energy partitioning between ascent and descent zones changes, and the ITCZ area simply changes also to compensate for the modified energy partitioning. So our focus here is to sort of derive an explicit expression for the ITCZ area as a function of the current climate properties. And what do I mean by that? So given a profile of, say, surface temperature, can we derive an explicit expression for, say, something like the area, at least the fractional area of the ITCZ, as a function of surface temperature and other properties of the climate state? And we do that here, but to do so, we have to make a lot of simplifications, starting with zonal and meridional symmetry. So zonal symmetry means here there's nothing varying in the zonal direction, so there's only one effective length dimension, so north and south. And meridional symmetry means, in this case, things peak are at the equator, and then they drop the same way in both the northern and southern direction. All right, and of course, this is where Arakawa's and Schubert's QE equilibrium or quasi-equilibrium hypothesis comes into play. So a lot has been said about this QE hypothesis, but the one line gist here is that it posits a statistical equilibrium between a slow forcing and a fast time scale consumption of whatever the forcing is supplying. That's here it's convection. And the time scale separation and the essentially the supply demand properties of this interaction give you an equilibrium. And you can sort of see this even in data, just using water vapor and precipitation data. So in red here is a PDF of column water vapor. And you can see the PDF has a mode, so it has a preferred state. And on top of this, if you overlay the precipitation conditionally averaged by column water vapor, you see this. And if you sort of, so you see not a lot of precipitation for dry values and strong precipitation as you go into the moist state. And if you examine this relationship in context of this mode here, you can argue that if the water vapor values are below the mode, you're essentially not precipitating in a statistical sense. But if you're above the mode, then you precipitate substantially. So our interpretation here is that this mode is sustained by this equilibrium between a slow forcing that tends to moisten the environment and a fast sink, which in this case is precipitation and the proxy for convection. And this mode is a manifestation of QE in action. And so we can use this property to divide the tropics. Divide the tropics into two zones. One is a moist precipitating zone. The other is a dry precipitating zone. Essentially, we are arguing that for values less than this mode, that you get no precipitation. Values above the mode, you get strong precipitation. And this is not merely an absurd assumption, as you can see from this plot here. So here is time mean precip again, and on top of this I've overlaid a single valued contour of column water vapor. So here the column water vapor appears to nearly bound what you would intuitively think of as the ITCZ. So this gives us grounds to investigate the dynamics of a moist area before we talk about a precipitating area. So that in the simplified model setup, the bottom left looks like this. So you have the red is the surface temperature forcing, and then from that we can derive we can say something about the column water vapor profile, and from which we can say something about the precipitation profile and therefore the width of the ITCZ. And we impose certain properties on this setup. So first is we deal with fractional coordinates. So there are no absolute distances, so everything is relative to the nominal equator. So the domain goes from negative 0.5 to positive 0.5. And then we also assume certain functional forms for the surface temperature as well as column water vapor. And we also neglect explicit rotation. 3 minutes?
Yeah, you have the questions.
Okay. Whoopsie. All right, so this is just for, again, I'm going to skip the slide. All right, so we have a simplified setup, and we need physics in it. So we have parameterizations, and these parameterizations, without going into too much detail, includes radiation, clear sky and cloudy sky radiation, convection, and poleward moisture export. So the domain is not closed, so moisture and dry static energy is allowed to exit or enter the domain, and we sort of parameterize this based on the profile of surface temperature. And the thing to note here is that these are all complex parameterizations, but we try to appeal to empiricism wherever possible, and also we've tied in an explicit dependence on the column water vapor and surface temperature. So if you know what the moisture is doing and the temperature is doing, you know the physics, basically. And this slide, I guess, the key thing here is that we have a simple equation which we can manipulate to get expressions for the ITCZ area. And the key parameter here to note is this thing called the gross moist stability. A lot has been said about gross moist stability in the tropics, so I don't have time to discuss this in detail, but in a single sentence, it measures the efficiency with which convection exports moist static energy out of convective columns. And it's a highly uncertain but also highly critical parameter in problems of this sort. And okay, so we can solve, and we get into quadratic, which gives you explicit expressions for the ITCZ area. Okay, so this is what the model looks like. So on the left is a series of surface temperature forcings going from cold to warm, and the black is sort of our control. And in the middle panel, you have the precipitation profile that we can solve for explicitly from the surface temperature forcing. And you can see that as your climate goes from warm to cold, your precipitation area narrows in area, and also your precipitation intensifies, so you get more precipitation per unit area. And we can also solve for the strength of the ascent and the descent. So there's air is ascending in the precipitating zone and descending in the dry zones. And so this model predicts a weaker descent in a warmer climate and a stronger ascent in a warmer climate. So all of this is simple modeling, but we can also say, we also try to ask what this model can say for more complex models. So we took a bunch of AMIP models, estimated parameters from the AMIP model, and generated a prediction for this ascent area change, which has units of percent per Kelvin, and regressing predictions from the simple model against more complex, direct computations from the AMIP model gives you this plot. So there's a fair amount of scatter, but there's also a modest correlation suggesting that this model, the simple model, has relevance more complex for understanding the intermodal spread in more complicated models. All right, on that note, I'll stop here and maybe, one last sentence to say that, Dr. Arakawa's work is immensely influential, and it's quite remarkable that even after half a century, some of his conceptual insights are still useful. Thanks.
Questions? Yes, Alex, let me come back to you.
Thanks, Tom. Thanks, Fiaz. So my question here might be hard to, I guess, answer maybe from your perspective, but climate models in a warming climate tend to have too much of a El Nino-like response.
Mm-hmm.
And we know that in the record it's actually becoming a little bit more La Nina-like or just staying neutral. So how much is the result of an intensifying narrowing ITCZ dependent on the representation of that? And what processes do you think, how would that be incorporated into your model, like single versus double ITCZ, for example?
Yeah, great question. So there's no ocean in the model. So you effectively give it a sea surface temperature forcing, and then ask how much of the area is occupied by essentially ascending regions. From that perspective, the model is somewhat agnostic to what is giving you the forcing. It simply gives you a solution for what is a simplified representation, the ITCZ. And so more complex dynamics, the model will get way more complicated.
Kerry?
I think you mentioned earlier in your talk that the two important feedbacks directly responsible for the narrowing are the moistening of the environment and cloud radiation feedbacks. If I understood you correctly, which one of those two, if either of them, turns out to be more important in your results?
So the answer depends on whether you're looking at inter-model spread like an AMIP or just absolute contributions to narrowing. And it turns out that there are multiple effects, and so these include the clear sky water vapor feedbacks, which are important, and the cloud radiative feedbacks are also important, and so is the gross moist stability. So there's no single answer. There's just a host of processes that interact with each other, and some of them turn out to be important for the intermodal spread problem. Yeah.